One, this is the final exam, or a mock final exam. As already mentioned to you, it's going to have parts starting from the planning lecture. And this is the structure. We're going to have MCQs, and every question will be on a topic: Bayesian network, Bayes rules, decision theory, game theory, planning. And then one problem on Bayesian network, MDP, game theory, and the code structure. So let's start by this exercise here. Consider a Bayesian network A. Okay, so we have this structure and this structure. A causes C and B causes C and C causes D here. So C is called the collider. You know, we have colliders, which are, we have three structures in Bayesian networks. What are the three structures? Fork, chain, and collider. And okay, this is a collider. Now, which conditional independent statements are true?
What do you mean by that conditional?
Completely independent. So this means A is unconditionally independent. It's independent. So is this true or not?
If C is non-independent.
Now look, C is a collider here.
Yes.
A unconditionally independent with B. Is this true or false? Okay, now to see whether it's false or true, we need to review what is a collider. So we have talked about colliders here in the D separation. So we have three possible structures, right? Chain. So we are in this structure, we're in the collider. And in the collider, if B is observed, so if B is observed, the path is blocked. And if B or its descendant, if B is non-observed, they are independent. And B or its descendant are observed, the path is active. So now, if I give you the following one, let me go here. Here, can we say that A and B are independent? So looking at the collider, so when this path is going to be active? Given C. Did I put here given C? No. So A and B are independent because we don't assume the knowledge of C. Now A and B independent given C. They are dependent. Now going here, if this is observed, the collider is observed, they become dependent. So here we cannot say that they are conditionally independent. Okay? Now A conditionally independent with B given D. Why? So the knowledge of D will also infer the knowledge of C, and the collider here will become active, so they will become dependent. Now this is the rule. Okay? B or its descendant. Now D, it's the descendant of C. And here, A and D conditionally independent on C. What do you think? A and D, so this is D. If I know C, are they independent? What is the structure between A and D? Is a chain. Look, A gives C, C gives D. So we have a chain. So if C is observed, now going to the chain rule, if the collider or the chain here is observed in the middle, then it blocks, so they are independent. Voila. So this becomes true.
But we said we can't assume the knowledge of C.
No, look, given C.
I can see.
Given C, okay, given C, because I didn't want to show. Okay? Now, can you see it? And are these conditionally independent? Unconditionally independent? Yeah, this is obvious, they are connected. They are connected, so they are dependent. Okay, so here I provide you the whole explanation. And in this solution, I provide detailed explanation. Doesn't mean that you have to provide all these details. I'm going to give you another solution answer. What is the minimal answer that can deserve a full grade? So you know what is the answer style. Okay, now the Bayes rule application. Imagine that you have something like this. Okay, let me move to this question. Read the question. Cybersecurity system. We have three values. P intrusion, 0.01. P alarm, given the intrusion, which is the likelihood. What is the probability to have alarm, given that there is an intrusion, 0.95. And P of the alarm, given non-intrusion, 0.05. And then we need to check all these values. So how do you proceed in this case? Yeah, we need to calculate. Now, كله مرتبط بهذا. Everything is related to this value, which we don't have. So you cannot just make a guess. You need to make calculation. Did we do something similar to this in the lecture? Obviously, yes. So now, going back to the lecture, and this was done in the Bayesian reasoning. Lecture 10. Yes, yesterday, last time. Yeah, last time we did this. So we're going to apply the same strategy that we have applied to solve these exercises. Okay, now you got the point. Coming back to the question, what is our evidence here? So I need to calculate this. So I have the alarm is the evidence, and this is the intrusion. What is the available values that they have? I have the prior, which is the base rate, and I have the likelihood. And what is missing? The probability of the evidence, the probability of alarm. Okay, so in this type of questions, you need first to make your calculations. You need to make your calculations like this. So, of course, the first rule that you will apply, what is this rule? What is this rule? What do we call this rule? The Bayes rule. Okay? Probability of the hypothesis given the evidence is equal to the following formula. The likelihood multiplied by the prior divided by the probability of the evidence. And the evidence is the alarm. What is missing in this information? So I have this probability, which is the probability of alarm given intrusion. I do have it. I have this probability, the probability of intrusion, which is the prior. So I don't have this probability of PA. What rule I should use to calculate the probability of A? The law of total probability. Mumtaz. So you must know this law. There are 3 or 4 rules, you must know them. So now to calculate this, I need to make an expansion. Probability of A, probability of A given I, multiplied by the probability of intrusion, plus the probability of A given not I, plus probability of intrusion, non-intrusion. And we do have all these probabilities over here. So usually the probability that we give as input, they will be used to solve any kind of unknown probability. Yes? Yes, obviously. And this is an axiom. You have 3 axioms in probability. The sum of probability is equal to 1. This is one of the axioms. The second is any probability is between 0 and 1. Okay? So doing that, you calculate first the probability of A, which is the evidence, and then you have everything to calculate that. So now I have this value, 0.16. So the questions become straightforward. Is probability of intrusion given alarm greater than 0.5? Obviously no. And the probability of intrusion given alarm is smaller than the probability of alarm given intrusion? Yes, because 0.16 is smaller than 0.95. And so here you cannot make just a guess. You need to make the calculation and everything becomes possible. The base rate significantly affects the posterior. So the base rate here is the prior. We call it also the base rate. Does it affect the posterior? Yes, obviously, because we divide by the posterior.
The base rate is the same as posterior?
Huh?
Base rate is
Yeah, we multiply by the posterior. So it's going to affect. So if the base rate is very small, the probability of the posterior given the evidence is going to be small as well. Okay.
I didn't understand what's the base rate.
Prior.
Right, no.
Yeah, it's the prior. This is the prior.
Evidence.
Not the evidence, the prior.
Right.
The evidence is the alarm.
Okay.
And the prior is the intrusion. Okay? Yeah.
Is option C dependent on the value of the prior?
Which one?
Option C.
Option C, yes.
Dependent on on the value of the fire, or is it always a given? It always affects.
Yeah, it affects. Look, it's part of the Bayesian formula. It's part of the Bayesian formula. So here we're going to divide by 100 if it is 0.01. So it's going to dramatically reduce. Look, significantly reduces the posterior despite high sensor accuracy.
So even if it's, for example, if it's 1,
Yeah.
can we say C is correct or no? If the value of the fire is equal to 1. Can we say C is correct?
Yeah, that's debatable. That's debatable. We can say yes and no. Depends on how we interpret it.
When we answer this question, do we answer based on this scenario or just in general?
On this scenario. On this scenario. But we're not going to give something debatable. Although I have some questions debatable here. I mentioned them, yes.
So we have to make the calculation and solve the MCQs.
Yes.
For grading, will we be graded like?
No, I'm not going to see, in MCQs, I don't see your values. So, okay, but I'm going to see your values in other questions similar to this one.
Can you see the values if we ask for
Huh?
the MCQs? Because sometimes you do the whole calculation well, but then you solve the MCQ.
Yeah, 113 questions to solve, copy to solve in just 2 days. It's going to be a little bit hard to focus. So try to be clear, and accurate. And what I recommend you to do, solve these type of questions 10 times. You must make at least 10 manual handwritten calculations at least 10 times. Okay, so you will work on speed and correctness. You must have speed and correctness to find time to reason, to think about the problems. Okay. Because this is very typical. I mean, everything is based on the bias. This is like straightforward. Bayes rule is unnecessary, of course not. This is completely false. So I'm going to stop here because, or decision theory, this is something I'm going to make it. Now, decision theory and MDP, in an MDP with a discount factor gamma equals 0.9, which statements are true. Now, what are the most important things we learn in MDP? What is discount factor? Do you remember what is a discount factor?
Yes, after like several times, it will be less than the value.
Yes, so how important we consider future rewards. So let me make a reminder. When we talked about decision theory, we talked about the discount factor. So you remember this use case? We're going to have a graph having states, chance nodes, and we have an action that you make a transition with a certain probability to any of other states.
Will we be asked to write scheme?
Yes, you can. Yes, they're going to be like MDP or Bayesian network. These are things like very common. So now, if you remind this one, if I put a discount factor equal to 1, so it means that all future discount rate will count in the same importance as our current. And look now, this is the row total, and this is discounted total. There is no discount. Now, if I reduce this to a smaller value, okay, the cumulative total will be smaller. Now, if I didn't put the discount, because future reward has less importance. So the first reward is going to have the same importance. But as we go deeper, this one, discounted total, will have smaller value.
Discounts 10%, not 90, right?
Yeah, 10% the year discount. So the discount factor is 90. Okay? It means we're going to multiply, the Bellman equation?
Yes.
The Bellman equation, you will multiply the future reward by gamma. Okay? And this is like the Bellman equation. This is the Bellman equation. Look, gamma multiplied by future rewards, which is the probability of transition to the state multiplied by the value of the state, the Q value of the state, and here the immediate reward. Okay, so now having understood this, if gamma equal to 0, the agent only considers immediate reward. Is this true? Only consider immediate reward, yes? No future reward. I'm going to cancel out any future reward. I just focus on my current reward.
Next will multiply by 0 and we
Yes. So every time you're going to accumulate only with the current reward. Yes, same reward.
can gamma be greater than 1? Because
If you put it greater than 1, you will risk the convergence. It's going to explode. So this is why, look at the next question. The Bellman equation, the value of the state is the max over all rewards plus the discount factor, the sum of future rewards. And this value converges for gamma between 0 and 1. Is this true?
correct, yes.
Yeah, this is correct.
discount value equals to, let's say, 0.10, does it mean 10% discount?
Yes, 10% discount. So I will account 90% for future rewards. If you discount 10%, you account for 90%. Okay, this is why we call it the discount factor. Okay, yani how, 0.9 important, not 100% important, 90% important. Yes.
Discount is zero, and we don't have future reward. It's only
The current reward. Yes.
only this one.
Yes, the accumulation of current rewards. Yes. So the value iteration and policy iteration produce the optimal policy. What is the difference between value iteration and policy iteration? So we covered them here. So in the context of policy value evaluation, we have an iterative algorithm that will calculate the Q value of a state. The Q value of the state, yani it's the best utility for that state. Okay, the best utility for that state. And the value iteration, we're going to calculate the best utility of that state for any type of action. So this is related to one action. If I take this action, what is the best utility I can get? And this one is the maximization across all actions. Okay, so the question here now, coming back to the question, the value iteration and policy iteration produce the same optimal policy.
No, that's not false.
Why? It's correct.
So we need the policy iteration to apply it based on each value iteration. So value iteration could give us the optimal value, and the policy iteration we apply it to all value iterations to get the optimal.
Yes, but
Optimal policy.
yeah, I know. Now you talk about the value itself, how it is calculated. But now we talk about the policy.
Because the policy is multiple values, right? It's multiple actions.
Yeah, multiple actions.
Value iteration is only one action.
Value iteration, you make it on a particular action. Yes. Policy iteration is basically just a generalization of this. So it basically uses value iteration, but on all possible actions. You see what I mean?
Yes, but so how can you say that they both give the same optimal policy?
Iterative policy evaluation. So yeah, this one, it gives the value for one policy. Yes, for one policy. The other one will give for all possible policy.
So I would think C is not correct, right?
Wallah, here it's. I see your viewpoint. I see your viewpoint. Homa, they don't calculate the same thing.
We
Like
can't find optimal policy without value iteration, but if we calculate value iteration only, we do not get the optimal
policy, yes. Yes. So that's debatable actually. Okay, so higher gamma close to 1 make the agent more far-sighted. ينظر المستقبل. Yes. So that's the opposite. In deterministic MDP, optimal policy is the same regardless of gamma. Of course no. Yes, of course no. Because gamma is going always to affect. It's going always to affect. Yeah, you look for the future. You look more for the future. So gamma, high gamma will let you also anticipate for the future. Because you will not discount the future. Okay? No problem. Okay, let me go to this exercise now. And this is very important. This is very typical. Which is about Bayesian networks. So here you will be requested to construct a Bayesian network structure and apply D separation. Do you remember these concepts?
Yes.
Okay, so here we go to Bayesian networks. And in Bayesian networks, usually we try to build a graph, an acyclic graph, where we have node and we have transitions. And transitions are represented like edges. So usually you need to make a Bayesian network representation as a graph like this. Okay, look at the question now. Given a company monitors the network security with different variables. These are variables that will affect our decision. So one of the variables is the network traffic. It can be high or normal. And usually, if there is a high traffic, we can suspect that there is an intrusion. صح ولا لا? Because intrusion, usually they try to send a lot of messages trying, for example, to pull the server down and making a denial of service attack. The intrusion attempt, actual intrusion occurring, we denote it as I. The system load, which is a server under heavy load. The firewall alert, F. It's a firewall that generates an alert. And log anomaly, which is the system log that show the anomalies. And then we specified different dependencies. And these dependencies are like the transitions. What affects what? What influences other events? Here, based on this description, we give you that I and S both cause high traffic. I, intrusion attempt, and the system load, they cause the traffic, the network traffic. The firewall depends on N and I. So the action of the firewall will depend on the network traffic and will depend on the intrusion attempt. And we have the log anomaly will also depend on I and S. These are the dependencies. The first question here, draw the Bayesian network structure. What are our nodes? These 5 states. What are our transitions? Our transition will be captured here. So usually now in the solution model here, I try to put a reminder about what concept you must know to respond to this question, and also a reference to the lecture. Now you can go to the lecture 11 part 1, slides 15 to 30 to review these concepts. And how to build a Bayesian network? Usually it's a direct acyclic graph. What is an acyclic graph? Doesn't have cycles. Okay? And you have the nodes represent random variables. These are our nodes. And the edges represent direct or causal probabilistic dependencies. Causal, what causes what? What influences other nodes or other random variables or random events? And the node is conditionally independent on its descendants given its parents. You know, the rule of conditional independence that we have introduced. يعني كل node فقط مرتبط is only dependent on its parent. And this allows us to write what? The joint probability, we write it as a product of conditional probabilities over the parents. Okay? As a simplification. You know, this is the concept of conditional independence. This is how we denote it, conditional independent. And this helps to write the equation what is the equation that we have written here? Yeah, joint distribution factorization. This one. This is the consequence of the conditional independence. The joint distribution, which is very complex to calculate, in the context of Bayesian network, where the kernel head of the Bayesian network is to reduce the computational complexity by considering the parent-child relationship between the event. Okay, and this helps us not to calculate the dependency among all nodes together. Okay, we reduce the complexity from exponential to be less complex. Okay, so now this is the background that you need to consider in the beginning, and then you start building your network, your Bayesian network. So now we're going to take statement by statement. Look, I and S both causes high network. This is given to you. And this will imply, you will draw an arrow, I implies N, and S implies N. Second statement, F depends on N and I. Look now, this is a causality, this is a dependence. Relax. F depends, is influenced by. Now, I and S influences N, and here F is influenced by N and I. So here I'm going to make N causes F, and I causes F. And finally, L depends on I and S, same thing. You're going to make I causes L and S causes L, and this will give you the following network. This is, you know, when you respond to this question, you just need to draw this one. You can make this computation on paper, I recommend that you bring a pen and a paper with a calculator. So you can do this offline and then just draw this in a clear manner. Okay? And look now, this is I implies N, I implies N, then you have S implies N, S implies N, and so on. And now we can identify, we have colliders. Look at this. This is a collider, this is a collider, this is a collider. Do we have a chain? We have a chain, S and F is a chain. So we need to identify this because now we're going to make inference, Bayesian inference, which is probability of a query given an evidence. And we will apply the D separation in order to check whether the path is active or the path is blocked. Yes?
This collide versus support.
Which, what, you know, N. No, I talk about N is a collider. Okay? I is a fork.
I plus support.
Okay? And then you have S. N is also a chain with respect to F and S. Okay? Depending now on the query, on the evidence, we're going to look on what is a collider, what is a chain, okay, and so on.
Why is L at the end?
Just I want to highlight these two colliders.
Why is F?
Yeah, just missed it, yeah. And look, I tried to put all the details. So later on, if you review, you can have all the information. Intrusion gives traffic, intrusion causes high traffic. This is the explanation of the edges, the explanation of the edges. So you must have this reasoning on your mind. You don't need to write it maybe. You need just to provide this one. This actually translates all the reasoning that you've made, including what topic to review and so on. Now the second question, let me just go to the question here. Are I and S conditionally independent on F? Use D separation. So what we should do here? How are you going to solve it?
Check the everything's unobserved, right?
This is observed.
Okay. So
Okay, if I say given, what is given is observed. Now we're gonna go here. Now if you have the amshay, if you make it wrong, it can have something wrong afterwards. So you need to make this right. It's simple, just logical reasoning about the causality between the events. And what do we have here? What is I and S conditionally independent given F?
No, it's conditionally independent. No.
We must make reasoning. How do we reason now? F is given, and F is a collider. صح ولا لا? Now, if F is a collider and is given, I and N becomes dependent. هذا the first statement. Now, if I and N become dependent, and this is a descendant of a collider, so the knowledge of F implies the knowledge of N, right? And I and S are related by this collider, which is known. So what does it mean? If this is known, is this path active or blocked? Huh? In a collider. Okay.
If we know N, then I and S are dependent. Yes.
We go to the collider. Where is our collider here? In the D separation. Okay, we have the rule. If B is known, they are independent. Okay, the path is blocked. Okay, so coming back to our solution here, if this is known, the path is blocked. So I and S are conditionally, the path is active.
Doctor, if you check the fork,
Sorry?
you check the fork on the collider. In the website.
To the D separation.
Yeah, the D separation.
But you're right.
You highlighted the fork, not the collider.
Yeah, this one. Okay. Yeah. If it is observed, the path is active. So they become independent. And this is our case. F is known. It is a descendant of N, which is the collider. Then I and S are dependent. So the response to the question, I and S are not conditionally independent given F. So how to respond to this? You can say F is known and it is a descendant of N, and N is a collider. So this implies N is known. In the context of a collider, okay, I and S become dependent. That's one possible answer. Okay, and this is a complete logical reasoning about how to do it. Okay, we have a collider. I and S is a collider, and given F, the path is blocked given F, because F is a descendant of N. So when we observe F, we gain information about N. So N becomes also known. And this will open the path. The path will be active for this collider. Does it make sense? Okay, look at this separation here. B or descendant are observed. خلاص هنا we can say very easily F is observed as a descendant of N, I and S becomes dependent. واضح؟ by rule. So I and S are not conditionally independent given F. Next question. Which node in this network is a collider and what happens when this collider node is observed? So of course here we have three colliders. Of course when the collider is observed, what happens?
It's active. The other two.
Yeah, the path becomes active and the node becomes dependent, conditionally dependent. Observing a collider opens the path between the parents, creating a dependency of non-existing before. And this is just more explanation about the topic. This is another also typical exercise. We're going to finish with this. A smart home system uses a monitor sensor to automatically control the lights. When someone is home, the motion sensor is more likely to detect the movement. تعرف motion sensor sometimes it can detect, sometimes it may miss. يمكن يكون a little bit far away where there is some kind of interference. And then when motion is detected, the light turns on automatically. So here, what kind of structure we have? You have a chain. And we have the probability of home. This is like the prior is equal to 0.6. And we have conditional probability tables. So usually when we give you these numbers, it means it will help you calculate some unknown probabilities based either the Bayes rule, the chain rule, the law of total probability, all these different type of rules. Okay, and now it depends on your query. It depends on your query, on your evidence. Now, given the light are on, compute the probability of home equal to true, given that the light are on. What is our evidence? What is our evidence? What is observed?
Lights.
Light are on. It means light are true. What is our posterior? Whether someone is at home. And a home equal to true. صح ولا لا? What is our hidden variable? Motion. Okay? And you have two different ways to calculate this type of probabilities. Okay, what are the two different ways? We have enumeration and value iteration. Okay? So enumeration is kind of feasible, but it's complex. I mean, when you have a lot of hidden values, the computational complexity becomes high because you need to calculate so many variables. So one optimization is the variable elimination algorithm. So let's first remind about this. Usually in enumeration, we try to solve the problem, what is the probability of a query given an evidence. So in our context, the evidence is the light. I know that the light is open, but how likely this light are open because someone is inside. This is our posterior. And to do that, I need to calculate the probability of Q given the evidence. I fix the evidence, but I have hidden value. I have information about the hidden variable, which is in our case the motion. So I'm going to make the sum of all possible probabilities based on the total probability law, divided by the sum over all hidden values and all the queries as well. And let's see how it works. So okay, let's see how it works. So basically we're going to same again use the Bayes rule. Bayes rule al asl. Okay, the probability of someone being at home given that the light is on is equal to the probability that the light is on given someone is at home multiplied by the prior home equal to true divided by the probability of the evidence light equal true. Now based on this Bayesian equation, what values are available and what values are not available? We have probability home equal to true is available. دائما in this type of question, make checkbox on what is available and identify what is not available to know what to calculate. Maybe if you don't know, you're going to try to calculate probability of home equal to true and it's already provided. You must know what is provided, what is not provided. So now probability of home equal to true is provided. Probability of light equal to true, is it provided?
No.
It's not provided, but I can find it because I have probability of light given motion. So I can make the law of total probability over these values and I can calculate it. صح ولا لا؟ مثل ما عملنا من قبل. And I don't have this probability as well, the light equal true given home equal to true. I have motion given home and light given motion. And motion is hidden. So I'm going to make the sum over all these hidden values to calculate this value. Does it make sense?
0.9 and 0.1.
Yeah, 0.9 is the probability that motion is true and home is true. And this is the probability that motion is true and home is false. And this is the probability of light is true and motion is true. And this is the probability. We have many combinations, but don't worry. Don't get distracted by these combinations. Just identify what you want to calculate. And then you will find the values that will help you to make the computation. Okay, now, if I want to calculate this one, I'm going to apply this formula, like we applied it here. Look, this was the hidden value we calculated for both flu is equal to yes and flu is equal to no. And here I'm going to calculate it for motion equal to yes and motion equal to no as well. هذا reasoning. Motion is hidden. So I'm going to calculate all probabilities whether motion is true or the motion is false.
If you want to calculate motion is false, we just subtract 1 from 0.95.
Yes. Look at the equation. This equation is what? I'm going to calculate the probability of light equal true for any value of motion multiplied by the probability of any value of motion given the home is true. Why I want to do that? Because here I have light given motion and I have motion given home. I converted this formula to get the value that I have from the hidden variables. Okay, I have all the values, the light equal true given motion regardless of the motion. Look now, light equal true, motion is true or false. I have it. And here, the probability of motion equal true or false given home. And I have it from here. So doing that, I can expand this systematically. Does this make sense? Okay, the probability of L equal T, M equal true, this is the first one, multiplied by the probability of M equal T, true, given that home equal true. Now, the second value in the summation, plus probability of L equal T, the same, look, this is the same, this is fixed, the evidence is fixed. And I'm going to change the hidden value, multiplied by the probability of M equal F. When you finish this equation, you will go to your tables and bring the right values. Now, this first value, from where I can get it? L equal T, M equal T. L equal T, M equal T, yeah, that's fine, 0.95. Now let's go to them, don't get distracted by this value. Only go to these values when you finish your equation. The equations are simple. You look for the hidden value, you expand your equation, and then you're going to make the mapping 1 to 1 from the table. Just be systematic. Just be systematic. And multiplied by probability of M equal T, H equal T, going here, M equal T, H equal T, 0.9. I'm going to put the number. Plus, light equal true, M equal false. Light equal true, M equal to false, 0.05. And probability of M equal to false, given H equal to T, I don't have it. M equal to false. What is M equal to false? Given H equal to T. Because here I have M equal to true and home equal to true.
0.6
Yeah, if I want to make motion equal to false, given home equal to true, 1 minus 0.9. Law of total probability, 1 minus 0.9. So it's 0.1 here. It's not directly provided, but the sum of all probabilities is equal to 1. 1 minus 0.1 is equal to 0. 1 minus 0.9 is equal to 0, 1, because you have this probability and you want to take the opposite of that probability. You have here MTHT, and I want MFHT. So it's one minus the other. 0 point. Okay, so in the exam, make the detailed equations. If there is simple computation error, we can be flexible around this. If your reasoning is correct. Okay? If your reasoning is correct, we can be flexible. So we calculated this one. Now we will calculate the second unknown value using simply the law of total probability. And the law of total probability, it's equal to this one which I have calculated before, plus this one which we need to calculate here in this step. And if you look at the example that you did in the class, it's exactly the same steps. Now, in order to get comfortable in the final exam with these type of questions, solve them multiple times. Multiple times. Solve them, look at the solution. Just forget about it, come after 20 minutes, 30 minutes, try to solve them again. And look where you get stuck. Every time, look what you get stuck. After 3 iterations, 4 iterations, it's like machine learning. You do multiple iterations, your loss will converge to 0. Okay? Your error is going to converge to 0. This is how you learn. It's with iterations. One iteration, give you some, only maybe partially. You can solve until step 2. Second iteration, you can stop until step 3, and so on. So do multiple iterations until you'll be able to do that computations. And we have several examples in the lecture, and this example here, I think that would be sufficient to be prepared for the exam. Now, the challenging part is the variable elimination. It's a bit challenging. And basically, the idea is we're going to calculate the same probability, but we try to simplify the way on how we calculate it. And if you remember, I gave you the analogy between how to calculate that probability. It's like, for example, in algebra, you want to calculate this factor. Instead of making all this combination, all this calculation, I think here we have 1, 2, 3, 4, 8 summations and 24 multiplication. Okay? We can just make it only 1, 2, 3 summation and 3 multiplication, which is basically factorization. We try to make factorization. This is why we try to find the factors, which are conditional probabilities, to simplify the way on how we calculate. The challenging part is on how to calculate the factors. And of course, there is systematic algorithm that we've talked about before. Okay, we want to just make the conditional probability of P given A. It's just like a factor of alpha multiplied by the joint probability P, B, and A all together. And we want just to get rid about the enumeration, because enumeration is going to calculate all the possible conditional probabilities, and we reduce that to factors. And we did a couple of examples in this lecture. So the variable elimination here, you can get back to lecture 11 part 2 and review the slides from 25 to 40. And the algorithm overview, it's an efficient algorithm for exact inference in Bayesian network. Instead of computing the full joint probability, the variable elimination works with smaller tables called factors, which we will calculate. So there are 4 steps. First of all, you need to create initial factors from the conditional probability tables. Second, you need to set the evidence by restricting the factors to observed values. And then we eliminate the hidden variables one at a time. And finally, we multiply the remaining factors and normalize to get the final probability. So let me take you about the steps. There are steps that are simple and some steps that require a little bit more attention. The first step is what? If anyone has something, you can go, but I'm just going to finish this part. So you need to identify what is your query, what is your evidence, what is your hidden variables. And I will say, if you do that, you get some partial grades. Okay? Now, my query is the following. What is home, given that the light is true, given I observe an evidence. Now, the evidence is fixed. And I want to calculate this posterior, given I have this evidence. It's the same as enumeration, but the way on how to calculate is going to be a little bit different. My evidence is fixed, the light is true, and I have the motion, which is the hidden variable. So from the CPT table, we're going to try to extract initial factors. And these factors are just conditional probabilities. Or the prior. The prior, because look, what is my prior? It's going to be related to my posterior. In order to calculate the posterior, I need to know the prior. So this is going to be my first factor. Your first factor is always the prior, and the prior should be given in advance. That's your first factor. Now, what is your second factors? It's the factor that depend on the hidden variables. Here we have a chain. We have home, motion, light. And my evidence is light, and my hidden value is the motion. So I can make a second factor, which is the probability of motion given the home. And this is given my CPT table. And the third one is the light given the motion, because I have a chain here. Okay? So these are our initial factors. And we're going to see if these factors are sufficient to calculate the probability. We're going to use them. Or if we need to expand a little bit more, we're going to expand them. So what do we need to do that? Look here, I have the probability of light given motion. I'm going to start from the last value, and it's like making backtracking until coming to the first prior value. So why I need to go to the last value? Because the last value is like my evidence. I need to start from an evidence. What is my evidence here? Light is equal to true. So I need to set the evidence light equal to true. We observe that light is equal to true, so we're going to restrict F3 to that particular observation. I'm not going to calculate the light given motion for any value of the light. I'm going to calculate the probability of light given motion for the light that I observed equal to true. So I'm going to just make F3 motion. I'm going to discard now the light because the light is fixed. The probability of the light equal to true given motion. And motion is still unknown, and it's hidden. Okay. So that's the second step. You can make it step by step. If you are not able to go to step 3, you have already made step 2. But if you understand the whole steps, that's fine. So now I have the F3 motion. What will be the value of F3 motion? We go to our CPTs. So probability of light equal true. I'm not going to invent everything. Probability of light equal true. I have two values already. ممكن أعطيك table فيه light equal to false, but you're going to select your evidence. Light equal to true, 0.95 and 0.5. I'm going to bring him over there. Which is basically, if motion is detected, 95% the chance the light will be on. If the motion is not detected, only 5%. Just the same CPT tables that we brought down. Now, I have a complete numerical validation of the first factor. Now, what I would like to eliminate? I would like to eliminate the hidden value, which is motion. So, to eliminate the hidden value, I have already calculated the value of F prime 3, and I have the value of motion and home. Look, probability of motion given home. And you will make the sum of all. What is the probability of F2 motion home? Is basically the probability of motion given home. Probability of motion given home, we have them from here. Okay, now if motion equal to false, you need to make 1 minus this value and 1 minus this value. That's probability. And you will have the following table. Look, home and motion both true, 0, 9. We're going to bring them from there. And this is the opposite. Okay, same thing. We have light equal to true given motion. We have already from them. We're going to bring them. And we make the product of all of this. And finally, we will make the sum for all motion values. Okay, look now. If you want to calculate F4 for home equal to true, I'm going to fix true, and I'm going to take these two values. صح ولا لا? Okay, it's basically probability of M home equal to true multiplied by the probability of light T equal to true, and this will give 0.85, 855, and plus 0.05. And the other one will be the sum of the two last remaining. So you just need to focus this a little bit more. Handwrite this a couple of times to understand the nuances, and that's pretty much it. If you make this, you have F4. Okay, we multiply the prior and normalize. we'll use the probability of home given the light. What is this value? Yeah, of course, yeah. So we're going to use this just a moment. The value iteration. We're going to just normalize among all possible values. This is for home equal to true, and you're going to also make for home equal to false. Home equal to false. And I need to make the probability with respect to all possible cases. So 0.512 divided by 0.512 is the normalization of the probability. And this gives me 90%, which is the same value as this. That's probably the most challenging topic in all the different other topics. الباقي الكل. So there are some exercises on Nash equilibrium. There are some exercises on planning. You know, it's basically straightforward questions, but maybe you forget most of this course content. I'm going to send you another version where I link every question and answer to the slides numbers. So you can go to the slide number, review from there. You'll have a summary of these topics. Okay, but repetition. You need to do multiple repetition.
The topics that will come in the exam, the same ones that are in the mock exam? This one?
Sorry?
The exact same topics as in here?
Yeah, but different questions.
Yeah.
Different combination. So it's not a matter of memorization. It's a matter of understanding how to solve these typical type of problems. You have also, you know, why I say, because there are a lot of concepts. Now, although I'm going to give you something like this one. Not exactly this one, because I'm going to remove some of the information that would probably help solving directly the MCQs. But I'm going to give you some equations. But you know, you must have them, you must have all these theorems, axioms in your mind. So just in case you forget how to make, for example, the marginal probability or something like this, you can have like a pointer. Yeah.
The separation, this one, will you keep it? 3 canonical structures.
Depends on whether I have MCQs that would, you know, I'm not going to give you answers that are directly related to the MCQs. But, you know, with the repetition, you don't need any cheat sheet document. Just, you know, every type of question, do it 2-3 times. I can send you some other combination of questions if you want to train more. But that's pretty much it. It's, you know, most of the questions are straightforward. This is just variable elimination requires a little bit of focus. There are so many, all the theorems are applied in one place. For the code, I gave some questions here about the code. Look, guys, if you want to have another either online session or physical session on Sunday, we can coordinate. Okay, we can coordinate to have an online session or a physical session on Sunday for the remaining part. So, for example, what kind of questions you can have? Look, for example, here. I can give you this code, and I tell you, does this code implement A star, UCS, greedy algorithm, or anything else?
But there's no writing, not coding, writing.
You know, I'm not going to give to write any code. Either you explain a code, I can give you why we have used this data structure in this code. Okay? Why, for example, in some data structure we use queues, and here we have heap data structure. You must be able to respond to this type of questions. And they built on your data structure course, but this is really important to know from programming perspective. No problem, you know, you want to use ChatGPT to explain me this code. You know, try to have like a summary of the code, understanding different parts, either in the knowledge base, in the Bayesian. Try to ask questions, why we have used this instruction. Is there any other alternative? You know, just have a general understanding about the code. Because, you know, if you do data structure, it's to use them in AI later on. Okay, in data structure, you'll have NumPy arrays. Did you do NumPy arrays in machine learning? Yes. This is data structure. Pandas for visualization. Yeah. So that's really important to understand from programming perspective. But writing code by itself, no. It's not writing code by itself.